So we're talking about power series, and last time we finished up with a bunch of properties of power series. So there were these properties of power series. Okay, and what they were telling us was that if summation a sub n x to the n, summation a sub n x to the n. If you have two power series, okay, if you have two power series and they both converge in some interval, negative r, okay, then a couple, there are a few things that are true, that the sum of the power series, if you sum the power series, then you get a new power series whose coefficients are the sums, right? If you multiply two power series, then you get a new power series where the coefficients are this sort of complicated thing, a sub k, b sub n minus k, k from 0 to n, n from 0 to infinity. Three, if you differentiate power series, summation a sub n x to the n, then you get n a sub n x to the n minus 1 from n equals 1 to infinity, and from 0 to infinity. Right? You can differentiate your power series term by term, and you can, last thing was you can integrate it term by term. That the integral of your power series is just the sum of the integrals. Okay, so these first two you want to think of as something like power series behave like polynomials. Power series behave like polynomials, and actually these last two are also along that line. That even though it's an infinite sum, you can just add the terms, right? Even though it's an infinite sum, you can just multiply the terms like you would multiply polynomials. If you're differentiating a polynomial, you can just do it term by term. Same thing here, you can do it term by term. Down here, you can, if you're integrating a polynomial, you can do it term by term, right? If somebody says, what's the integral of x squared plus x dx? Well, you would just say, well, that's going to be x cubed over 3 plus x squared over 2 plus some constant, right? You can just take the integral of each term, right? And what these are saying is that even if it's an infinite sum, right? Even if it's an infinite sum, like x plus x squared plus x cubed plus x to the fourth, blah blah blah. As long as you're in some range of convergence, then you can just integrate term by term. Okay, so you can integrate term by term. Okay, so maybe now is a good time to give an example. To give an example of that. Okay, yeah, I'll do an example of this last one. Okay. So, for example. No. Before I get there, I want to say one thing which I didn't say, which was you get these new power series. Okay, you get these new power series, and the thing to notice is that further, the radius of convergence doesn't change. Radius of convergence doesn't change. Okay. So this is an important fact. Okay. Right. You might be worried that you get some new power. You get when you differentiate. Who knows? Maybe the radius changes. Right? Maybe the radius shrinks or something like that. But in fact, there's nothing to worry about. Theory, which we will not get into, shows that the radius of convergence is going to be the same. Okay, so if these guys converge in 1, 1, then the derivative is going to converge in 1, 1 also. Okay. So yeah, actually, let me give some examples of this theorem. Okay, so first, let me give an example for number 2. Okay, so wait a second, we can't do it yet. We can't do it. We can't do it yet. Okay, no examples. No examples. No examples because we don't have any good examples in some sense. Okay, so yeah. So let me wait until what we're going to do right now is create a bunch of examples. Okay. 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 So okay. So last time we had some power series, and then we said, oh look, this power series turns out to be this function, right? You remember at the end of class last time we were doing this game where we saw that at the very end we saw, for example, that the arctan was the sum of some power series, right? There was some power series. We had some power series expressions there. Okay, and those those were nice, but now what we're going to do right now is give you some way of creating the power series. Okay, so last time we sort of started from the series and then went to the function, right? And this time what we're going to do is, given a function, how do you find its power series? Okay, okay, and the topic is called Taylor series or Maclaurin series. This is actually 8.7. Taylor series, or also called Maclaurin series, depending on where you're doing it. Okay. So the problem is, given a function, what is its power series? What is its power series expansion? Okay, so so here's the idea. Okay, here's the idea. You have some function, and then what you do is you say, let's pretend it has a power series expansion. Okay, so given a function f, and say we want to, suppose we want a power series expansion. Suppose we want a power series expansion about 0. Okay, so we want some expansion like summation a sub n x to b. We're wondering if it has a power series expansion, what it is. Okay. So you say, okay, let's pretend that it actually has a power series expansion. So pretend f of x has a power series expansion a sub n x to b. Okay. Okay. And then figure out what the coefficients must be. Tom, do you have another marker? I think I left the marker you gave me yesterday. I left it in the other room. Thank you. So figure out what the coefficients have to be. Okay, and here's how you do it. You say, well, how? Here's how. you say, well, if I evaluate the function at 0, what do I get? So here's the sum from 0 to infinity. Okay. Here's this thing from 0 to infinity. F of suppose, what happens if I plug in 0 to the power series? What do I get? No, you don't get 0. You actually get, you're almost right. Almost everything turns into 0. But the 0th term doesn't become 0. What do you get? You get x to the 0, which is 1. So you get what did you say? Nothing? Who said something? No? Di Jialo. A-n when n is 0. So you're going to get a0. Let me show you. So right, this is a0 plus a1x plus a2 x squared plus et cetera, right? If you evaluate this thing at 0, what do you get? You get the a0 term, right? You get the a0 term. Okay. So if you have this function, you think, well, if it has a power series expansion, I know what its 0. I know what the a0 coefficient is. It's going to be the function at 0. Okay. Now, how am I going to figure out a1? Well, if I take the derivative of the function and evaluate that at 0, what do I get? Suppose I differentiate my power series, evaluate that at 0, what do I get? And see, close your. Oh, it's a book. Close it in. Thanks. Okay. So, what if you take the derivative of the power series and evaluate it at 0? What happens?
A1.
You get a1, exactly. Okay. How do I get a2? It's obvious. I'm going to take the derivative again, evaluate at 0, and what do I get? Do I get a2? Please say it. You said it, I think. You get 2 times a2. Okay. You don't get a2. You get 2 times a2. But at least you can figure out what a2 is. You just take the second derivative, evaluate at 0, and then divide by 2, and that tells you what a2 is, right? So we know that a2 is the second derivative at 0 divided by 2. The third derivative is going to give me what? 3 times 2, a3. Right? The fourth derivative evaluated at 0 is going to give me 4 times 3 times 2, a4, et cetera, right? And so what you see is that if f has a power series expansion, then summation a sub n x to the n. So there's a power series expansion around 0. Then a sub n has to be the nth derivative of f evaluated at 0 over n factorial. Okay, so just by this game of pretend, right? You say, let's pretend that that f has a power series expansion. Let's pretend that f has a power series expansion and figure out what would happen if it did have a power series expansion. In that case, the coefficients are going to be f, the nth derivative of f evaluated at 0 over n factorial. Okay. Okay. So right. So for example, suppose we have f of x is e to the x. Okay. Take 1 minute and see if you can figure out what the power series expansion of e to the x has to be. if there is a power series expansion, what is it? Okay, if you know what you're doing, you should already be seeing the pattern. So talk to somebody, turn to somebody nearby, and talk with them. Wang Di, how could you talk with Wang Qingshao? That's okay. Talk with each other. He can talk to you. Okay, so what is it? Can somebody tell me? Who can tell me? Anjing, how about you?
Oh, yes. Please,
You cannot speak at all. You can. Okay, Jin Xiaojing, please tell me what Anjing is thinking.
It's empty.
It's empty. Oh, it's empty. Okay, very good.
In my mind.
Okay. Somebody. Wang Qingchao, how about you? No idea. Oh, really? Okay. So maybe people aren't getting it. If there's a power series, right? If there's a power series, the zeroth coefficient is just going to be the function evaluated at 0. Okay. So you say, okay, I'm going to take my function and evaluate it at 0. I get e to the 0. That's 1. Okay. Then the second so the zeroth coefficient is the function evaluated at 0. The first coefficient is the derivative evaluated at 0. The second coefficient is the second derivative evaluated at 0 divided by 2, etc., etc. And there's this thing that happens, right? The nth coefficient is going to be nth derivative evaluated at 0 over n factorial. Okay. So you say, okay, well, in that case, I need to take derivatives and evaluate them at 0. But for this guy, whenever you take the derivative, nothing happens, right? So all the derivatives evaluated at 0 are 1, right? Right? They're all 1. Okay. So what does that tell us? The 0th coefficient is 1. The first coefficient is 1. The second coefficient is 1 over 2 factorial. The third is 1 over 3 factorial. The fourth is 1 over 4 factorial, etc., etc. Okay. So the point is that if there is a power series expansion about 0, it must be 1 plus 1x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed plus 1 over 4 factorial x to the fourth, etc., etc. That is summation x over x to the n over n factorial as n goes from 0 to infinity. Yeah, Wonky.
I don't understand how we get the factorial from the EX.
So that's the factorial comes from what we were thinking about here. Okay, so remember how we got this. We say, suppose your function looks like an infinite polynomial. So let me do it again. So suppose your function actually is some sort of infinite polynomial. Okay. Suppose your function is an infinite polynomial. What are the coefficients? A0, A1, A2, etc. What are the coefficients? Okay. And you say, well, look, well,
What do you mean by coefficient?
A0, A1, A2, A3. So you have a power series expansion, and you're wondering. Remember, for example, yesterday we know that 1 over 1 minus x is 1 plus x squared. Whoops, 1 plus x squared plus x cubed plus etc. Right. We saw this. This is the geometric series expansion for x less than 1. Right. So this function has a power series expansion. Right. This function has a power series expansion. Yes.
I don't know.
Okay. So what do you know what a power series is? Okay. So when I say it has a power series expansion, I mean this function equals some power series. Right, here it is. Right, here it is. This is a power series. Right, this function equals this power series. Okay, so this function has a power series expansion. Right, it can be written as a power series. Okay, and now we're saying, suppose you have some function whose power series you don't know. Okay, and you're wondering, does this function have a power series? If it does, what is the power series? Okay, so you say, suppose this function is a power series. Suppose there's some power series, right, that equals your function. How would you figure out what the a sub n are? Right? How would you figure out what the a sub n are? Well, you say, well, look, if I evaluate my function at 0, then I'm going to get a0 plus a1 times 0 plus a1, a2 times 0 plus blah, 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 blah. Right? Is that clear? Okay. Right, so a0, that tells me what a0 is. a0 is just my function evaluated at 0. Okay, so I know what you can figure out what a0 is. If I take the first derivative and evaluate it at 0, what do I get? I'm going to get a1 plus 2a2 times 0 plus 3a3 times 0 plus 4a4 times 0, etc., etc. Right? So that tells me that a1 is going to be the first derivative evaluated at 0. Right? Right? And you keep on going like this, and you see that the nth coefficient of the power series has to be the nth derivative at 0 divided by n factorial. You're wondering about the factorial. Okay. do you see how the factorial comes out of here? Right, if we take the second derivative, of this, right, we're going to get if we take the second derivative and evaluate it at 0, we're going to get 2a2, right? If we take the third derivative and evaluate it at 0, we're going to get 3 times 2a3, etc., etc. So the factorial starts showing up. This is 3 factorial. Okay. Is it clear or is it not clear?
It's clear.
Is it clear? I feel like you're lying. Are you lying?
Yes.
You are? You are lying or you're not lying?
No.
Okay. 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 So let's get back to the main stream of the story, basically. Okay. So you have your function, and you think, I'd like to get a power series expansion of it, and then you think for a little bit, and you realize that the nth, if it has a power series expansion, this is going to be its nth. This is going to be its nth coefficient. Okay. So we call, so definition, we call summation fn 0 n factorial x to the n from 0 to infinity. We call this thing the Taylor series expansion of f around 0. So you start with your function, you create this power series, and you call that thing the Taylor series expansion of f around 0. This term Taylor series is basically just say power series. If you say power series or Taylor series, it's the same thing. Okay. This is also called the Maclaurin series. If the expansion is around 0, then it's called the Maclaurin series. Okay, I think this is all kind of dumb, right? Why have so many names for the same thing? If you just say power series, that's fine. That's fine. Power series or maybe Taylor series. Okay. So back to this example, right? Here you have the exponential function. Here is its Taylor series expansion around 0. Here is its Taylor series expansion around 0. Okay. Let's do one more. Okay. Suppose f is the sine function. Okay. Suppose f is the sine function. What's the Taylor series expansion around 0? Okay, so again, if you know what you're doing, this should take you about 1 minute. 1 minute or maybe 2 minutes to figure out. Okay, so take 2 minutes and see if you can get it. So it starts repeating. Yeah, it starts repeating. Yeah, so just use those coefficients in the expression. And it's going from 1 to 1. So that's just right. So this is going to be n is 0. Plus the next is times 1. Goes to 8. So just use these numbers.
Oh, so this one is
Exactly. Yeah, so you're going to get 0 plus x plus 0x squared minus x cubed over 3. That's all. Okay, turn to somebody nearby and say what's going on. What's the expansion? Okay, who would like to? Okay, who would like to tell us how to do it, or what did you get? Somebody tell me what you got. What do you get? Good. That is it. Perfect. Right. Right. So you get only odd